I'm asking you to predict what is the major product for each. So this is where we need to think about the mechanisms. The bromine with the light, that will be breaking the bromine molecule into the bromine radical. That's the initial step. We got the bromine radical forms. That will go into the first propagation step, right? Meaning that it's going to be abstracting the hydrogen from the carbon. The question is, this molecule has a more than one type of hydrogen, right? So that's something that you better think about. Which hydrogen will that bromine will take out? That will make a difference. So that has to be related to the solving this question. So first thing is, there are hydrogen at that position, and then why we call these hydrogen, I pulled this one out, is because it's primary carbon. Right? If you remember that, the carbon, hydrogen on carbon, the typical, what we talked about, the degree of substitution makes a different radical stability. More substituted carbon makes a more stable radical. So this is a primary carbon, the least substituted carbon. There are hydrogen there. There are many hydrogen, actually 9 hydrogen for the primary carbon. There are also the secondary carbon here. This carbon has 2 carbon substituents. There are 2 hydrogen in the secondary positions, but this one has something called a tertiary carbon. This carbon has a 1, 2, 3 carbon substituents. So we call this carbon tertiary carbon. That's a tertiary hydrogen. Right? Bromine can take either. So let's go one by one. Bromine pick this hydrogen and then making this primary carbon as a radical. I mean, this radical can go there too. It can be there, but all of them are going to be primary radical. I just put only one here. I hope you recognize how to draw the arrow with a single electron move. It's a physical arrow, right? One electron comes in, one electron from that. That's what's the HBr. I didn't put the HBr because HBr is not an organic molecule, so I care less. It's organic chemistry, so I don't care about the HBr. I know it forms, but who cares? We care about the carbons. Carbon getting radical there. So that for physical arrow go to this carbon, that is 1 electron go to this carbon, that radical there. Right? That's how you draw the arrow of the radical reaction. Secondary radical, the same thing. If the bromine comes, pick up this hydrogen, 1 electron comes in, 1 electron of this bond comes out, making HBr. 1 electron go to this carbon, make the carbon, this carbon, secondary carbon, bearing a radical. That is a secondary radical. This hydrogen at the tertiary carbon. Bromine, pick up this hydrogen, then you're going to get the radical, the tertiary. So first propagation step of this molecule can potentially produce 3 different types of radical. Of course, the primary radical can be here or it can be there, either here or there, because the symmetrical doesn't really matter. So we can have 2 different types of primary radical, but they are primary radical. I'm only trying to represent primary radical here. This out of this radical, we go for the second propagation step. Is radical pick up the bromine with a 1 electron given here, 1 electron comes out, it makes a bond. The carbon with bromine bond. It forms a bond there. It releases a bromine radical that goes back to first propagation step. But we don't care about that because we only care about the product. This secondary radical at that position will pick up the bromine, will make a bromine goes to that carbon, secondary carbon. This tertiary radical will get a bromine, and then bromine goes to the tertiary positions. So the question is, which one is a major product? We need to pick either of those 3. But how are we going to pick those one of the 3? What should be the rationale of picking the 1 out of 3? So the issue is a more abundantly formed radical will make a major product, right? So which radical species out of those 3 will be formed more? Is this one, that one, or that one? So I didn't explain why it is, but we talked about tertiary radical are more stable then the secondary radical, then the primary radical. This is the most stable. If it's the most stable, it probably will be formed better because it's easier to be formed. So this will be the major amount of radical. And then this will, once if that form as a major, that will make this as a major product. So that is what you need to do to solve this particular problem, which is a not that difficult once you know, but you still have to chase every loose end and figure out which way things most likely happen. And then you gotta relate it to the structure. So that's something that you need to do right now. This is a very simple. We're gonna ask same question at the end of the organic chemistry 2, and then I'm gonna add another factors which can switch the result completely different way, but we're gonna worry about that at the time, not right now. So there's something more to come.
So is assumed tertiary is always the most stable, or is it a case by case basis?
Very good point. Just bear with me for the next example. Then I'm going to tell you the first tertiary radical is not the top of the list. I mean, of course, it is a good one, but there is something can be better. I mean, someone can already imagine. All right, second one. Same practice. Bromine with a light makes a bromine radical. What this bromine radical does is going to pick up the hydrogen from the molecule given. We can look at the molecule and where the hydrogen is. And then you're going to find out, sure, there's a primary position, and there's a primary carbon. Most likely, you think that's not going to happen. Once you see this, yeah, we don't normally care about the primary because it takes a more unstable radical, so, probably not the best route to do. Anyway, there are secondary carbon right there. So secondary, because this is a carbon with a two carbon substitute, that's why secondary carbon. So there's a hydrogen there. But if you look at that, there are other secondary carbon also exist, which is that this carbon has a 1 and 2 carbons there. So we can call that one secondary carbon. That's the same thing. This hydrogen is a secondary carbon. That's a hydrogen secondary carbon. But this is something that I really have to stress it out. All the reactions that we're going to talk about in the test 2, meaning that not only the free radical chain reactions, but also all the reactions in the next chapters, not subject to sp2 hybridized carbon. This carbon is sp2 hybridized, that's sp3 hybridized. These carbon hydrogen bonds are more stronger than that one, so you don't get the radical form at that position at all. No sp2 carbon will go through the reaction, not only this chapter, but also the next chapter. Okay, so don't try to do anything with this hydrogen on double bonds. That's not the hydrogen be taken out by the radical. The bond is just too strong because it's sp2 hybridized. All right, don't make a mistake there. Anyway, so that means that we got only secondary carbon coming from that carbon. There are some people, the tertiary carbon. This carbon has a 1, 2, 3 carbon substituents. It's a tertiary carbon. That's a tertiary carbon. We got 2 of them, but you can see that there's a symmetry going right there. So these hydrogens are equivalent to that one. This is equivalent to this one. So we got primary, tertiary, secondary carbon, just like what we saw before. So we can practically do the same thing. If you take the primary hydrogens out by the bromine radical, you are forming the radical at the primary carbon, either here or there, right? If the secondary carbon lose a hydrogen, that you're going to form the secondary radical like this. If the tertiary one taken out, that you're going to make a tertiary radical. We already know primary is not good, secondary is better than primary, tertiary is better than secondary. Most likely it's a tertiary, that's the reason. But there's extra things that can stabilize reactive intermediates. That is resonance structures. This one next to double bonds. So what is radical or positive, negative charges next to double bond does? It makes a resonance structure. It's like a hot potato. It can spread around those in the large areas. So each one can feel less. That's basically why the resonance structure helps. By making a resonance, I mean, tertiaries are already stable, but it makes the resonance structures, it makes it even more stable. In fact, you get the tertiary radical, somehow the secondary radical making a resonance structure. Output the secondary radical which are making resonance structures are more stable than the tertiary radical without. So stability of the radical is the key to solve a problem like this. So anyway, this one, the radicals on this carbon, initially we start from that, but double bond, one electron from double bond come in, so that makes double move to there. And that makes this carbon being a radical. In fact, half radical there, half radical here is actually one here. I mean, not exactly half radical, close enough. We can probably discuss about that later. So you can imagine that that's a more stable radical species, either because I didn't change one, I didn't pick one, because this is a resonance structure. There's no way you can have this one without that one, right? These two comes together as being resonance structures. You know that neither are real. Real things are something in between, reflecting this characteristic and that characteristic at the same time. That's a resonance structure. You only draw the two structures to show the glimpse of that, to extreme cases of that. Anyway, that leaves the products of the bromination at one position. You'd think that that's probably not going to happen. Secondary carbon can be brominated too, but that's probably not the major product. Major products, this tertiary carbon getting a bromine and making products there, you most likely, sure, that's the major product. If you only do that, I'm going to say you only get the half credit. Why that's not all the correct answer is radicals are 50% there, 50% here. That can also contribute to the products, different product. So major product is actually both, not one.